So as we have learned from the study of this Kobayashi-Maskawa theory, which had been experimentally verified, the quarks don't seem to be able to do this job. We need some much bigger difference between the behavior of matter and antimatter, that you can explain the difference between them so that universe annihilate matter and antimatter, we end up with tiny excess matter at the end of the day. So what could have been the possible particles that could have created this difference between matter and antimatter? So the idea is that now there's a new paradigm. Maybe neutrinos had been responsible for this. And it turns out that neutrino is a very good candidate for this, because what we need, one condition, is that matter and antimatter can be shuffled against each other. Now, neutrino also seems to have a very strange property which is helping our case. So one thing we have learned is that neutrinos can actually change, possibly, between matter particle, namely neutrinos, and antimatter particle, namely antineutrinos. We have seen that yet, but the only neutrinos can actually do it because the neutrino doesn't carry electric charge, antineutrino doesn't carry electric charge either. -0 is the same as 0. So the neutrino can, in principle, turn into antineutrino and back, and that would help us reshuffling matter and antimatter. And this idea came out from the two gentlemen, Fukugita and Yanagita, and became one of the very popular paradigms to explain why we exist, why there's only matter in the universe, but no antimatter. So first of all, we already know that neutrinos actually morph in a very funny way. And this is an experiment I was also involved in called CAMLON, and that is also underground in Kamioka. It houses 1 kiloton of mineral oil instead of water, like in Super Kamiokande. And mineral oil can be actually doped with other material to make it light up when there's some interaction going on inside, called liquid scintillator. And this is actually much more sensitive to much lower energies than water tank can be sensitive to. And that was very useful for the study of neutrinos. And this experiment could detect neutrinos coming from nuclear power plants all over Japan. And they were in operation when the experiment started. Of course, most of them have stopped after Fukushima incident. And let's see what happens afterwards. But anyway, these nuclear reactors produced actually quite a few of neutrinos, which had been detected in this Kamioka mine with CAMLON experiment. And by studying these neutrinos, this experiment could really show that neutrinos morph from one species to another. So just like in the case of other particles that we have seen, as predicted by Kobayashi-Maskawa theory, there are again 3 types of neutrinos, and they are named electron neutrino, muon neutrino, and tau neutrino, but names don't really matter for the purpose of discussion here. Important thing is that as time goes on, imagine this is a time axis, the produced neutrinos, this is 100%, would start to actually disappear, and that's the start of oscillation of neutrinos. And once they disappear, they actually come back and disappear again and come back. And you see neutrinos really oscillate. So this happens because the produced type of neutrino from the nuclear power plants now turn into some other species, which CAMLON cannot see, but then come back, which CAMLON can see, and disappear again into other species, which CAMLON cannot see. That's why you see this modulation or oscillation of neutrinos as a function of time. So neutrinos morph from one species to another, and the leader of experiment is Mr. Inoue. I played some small part, that's why I put picture in a much smaller size. And so because the neutrinos have this very funny property that it can morph from one species to another, that gives us some sort of hope that the neutrinos can also morph from matter version into antimatter version and vice versa. And now the same experiment CAMLON is looking for such a phenomenon. So if you have some biggish nuclei, like xenon, and then the neutron inside the nucleus might want to decay, called beta decay, a neutron converts into a proton. And if it does so, you have to change the charge, so it spits out an electron. At the same time, it spits out an anti-electron neutrino. But if the anti-electron neutrino is the same particle or can turn into an electron neutrino, namely this anti-neutrino can turn into a neutrino, then neutrino can be absorbed by another neutron, turning into proton, spitting out another electron. Then this is possible only when the anti-neutrino can turn into a neutrino. And this process called neutrino double beta decay. We know already that this kind of process can happen only once in 10 to the 24 years, a trillion years. We can't wait that long. But if you actually collection of these xenonuclei, let's say 10 to the 24th of them, then this process may happen once a year. So this is the way we want to look for the reshuffling between matter and antimatter. At the same time, and you actually need a big experiment for this purpose because you need to collect this many xenon atoms to look for this kind of conversion. At the end of the day, a xenon nucleus would turn into barium nucleus, splitting two electrons. So what you can do is in this tank of the mineral oil or liquid scintillator, you suspend another balloon, which also has the liquid scintillator in it, and you dissolve gaseous xenon into it. It turns out that xenon can dissolve into mineral oil. And now we have 100 kilograms of enriched xenon, and it has the best lower limit on the possible lifetime of this process. So namely that it actually happens less than once in a 10 to the 25 years. It happens only possibly once in 3.4 times 10 to the 25 years. And we are still improving this experiment further, looking for this possible reshuffling between matter and antimatter. But as you know, that couldn't be the whole story. Just like what we did with this E plus E minus experiment, looking for the difference between B meson and anti-B meson, we should also look for the difference between neutrino and anti-neutrino. And one way we would like to do so is by shooting the beam of neutrinos over a long distance. You can shoot neutrinos. You can also shoot anti-neutrinos and look at the behavior. And as we just talked about, one species of neutrinos can morph into another species. We try to measure this probability with neutrinos. But then you can also measure the same probability for antineutrinos and compare them. And if they are different, you have found another possible difference between the behavior of matter and antimatter. So that behavior could explain the origin of matter in our universe over the antimatter. And indeed, this kind of experiment is happening. You again need a powerful accelerator here, and using the accelerator, you produce a beam of neutrinos, shoot them towards Super Kamiokande experiment about 300 kilometers away. And what you do then is try to use the long distance to see the neutrinos convert into different species and antineutrinos convert into different species. And there's a similar idea of trying to do this experiment over even longer distance of about 1,300 kilometers in the United States. US is a big country, again, support this kind of long baseline. And there's a big powerful accelerator at the Fermilab in Illinois. And a target may be built in a Homestake mine in South Dakota. So this way, you hope to discover that the behavior of neutrinos and antineutrinos are subtly different from each other. And if the neutrinos can also convert into antineutrino as being looked for by Cameron and many other experiments, putting two and two together, maybe you can prove that neutrinos indeed were responsible in creating excess matter over antimatter so that we could survive the Big Bang. So this kind of study, if it would succeed, would really bring us to the earliest moment of the Big Bang. So using dark matter, we think we can go back to the moment when the universe was 10 billionth of a second old. Using the Higgs boson freezing into the empty space, we are probing the universe when it was only a trillionth of second old. But if this idea bears up the experimental scrutiny, then we have now provided a seed for antimatter to disappear at the end of the day when the universe was only 10 to the minus 26 seconds old. And this hasn't happened yet, but people are working very hard trying to probe how the antimatter has disappeared so that we can live in the current universe without worrying about getting annihilated by the bombardment of antimatter.